CodeX session series. It's truly exciting to see so many of you continuing this journey with us. Your commitment and consistency are what makes this series so impactful. IEEE CodeX Sri Lanka is a national initiative under the IEEE Sri Lanka section, committed to building a strong and inclusive community of students passionate about competitive programming and real-world problem solving. I'm Senaya Bandar, your moderator for today's session in the CodeX Sri Lanka team to guide you through another impactful and practical session that builds on everything we've learned so far. Before we get into today's session, let's take a quick look back at what we did last time. On 17th of July 2025, we hosted our third official session, which brought together 70 plus undergraduates from across Sri Lanka. Led by Mr. Lakshith Nishshanke, it was a powerful session packed with theoretical insight into sorting algorithms and binary search, two foundational techniques in competitive programming. The session was not only informative but also highly interactive, sparking active engagement from parts groundwork from research, which are IEEEXtreme and ICPC competitions. Today, we are taking that foundation one step further. Tonight, we move into the second hands-on session where we will be practically implementing and strengthening our understanding of sorting algorithms and binary search. These concepts form the backbone of many coding problems and are critical in optimizing solutions for real-time challenges in competitive environments. Mastering these through practice will elevate your confidence and speed as a problem solver. Before we move into today's session, we'd like to make a quick announcement. As you all know, certificates of appreciation will be awarded at the end of the CodeX session series based on your attendance and engagement throughout the program. To facilitate this, we kindly request to rename yourself using the name you used during registration. This helps us accurately track your participation and evaluations across sessions. It is with great pleasure that we welcome back a familiar face, Mr. Lakshith Nishshanke. He currently works as an engineer at ZEA and is a top-ranked competitive programmer, having secured rank 2 in Sri Lanka at IEEEXtreme 18.0. With proven track record in both national and international programming contests, he has also represented Sri Lanka at the International Olympiad in Informatics. We are truly privileged to have him with us once again, bringing his experience and insight to help us strengthen our foundation. Please join me in warmly welcoming Mr. Lakshith Nishshanke back to CodeX Sri Lanka. Over to you.
Hi, hello everyone. Uh, yeah, I hope everyone can hear me and see me. So let's get started. Okay. You guys can see my Safari screen, right? Yeah, I actually forgot to make a presentation. I, I, I think this is a hands-on session. We won't need the presentation. Hey guys, give me a minute. This is hands-on session. Okay, so our like theory session we discussed about sorting and binary search. We discussed some things about sorting algorithms and then a little bit about binary search. So the goal today is like solve some past problems in those topics. So I have picked two problems. One from sorting and one from binary search. So the thing about sorting and binary search is, first of all, like I said in the theory session, sorting is like a fundamental step in problem solving. So even in hard problems, you will have to uh, sort your numbers. Like if you have a list of numbers, you'll probably have to sort it. If there are problems like if the problem is like primarily a sorting problem, chances are it's like an easy problem. And also, but by also tend to be like relatively easy. I haven't seen like really hard problems from either of those topics. I mean, for hard problems, you might have like sorting or always have to use it. And it's then there are more like steps in like large algorithms. Yeah, I also got a message saying my internet connection is unstable. So if I drop or you can't see the screen properly, let me know. How can I open the chat? Okay, I have the chat open. So if something's wrong, let me know. Okay, so I picked two problems. First one is not this. Let's first start with the sorting problem. This one, I think. Yeah. Okay. If you guys want to open the problem statement, I'm gonna share the link in the chat. Okay. I'll send it in the meeting chat. Okay, let's read the problem. And also, in the first session I did, I explained a little bit about like in the introduction to computer programming session, I explained a little bit about like how to read problems and stuff. So let's follow those practices. Okay, so problem name is hotel wiring, and the time limit is 2 seconds, and the memory limit is 256 megabytes. It is standard. Okay, so the problem. A construction company has decided to let an inexperienced electrician work on power supply wiring for their newest hotel building. After the construction and wiring of the building has been completed, that the electrician. Okay, so I said some problems have stories and sometimes they're irrelevant. This first paragraph, it's kind of irrelevant. The hotel consists of M floors, and each floor has N rooms. Power supply room is controlled by one master switch on each floor. By design, power is supplied to all the rooms on the floor if and only if the master switch of that floor is on. Okay. However, due to the electrician's mistake in wiring, some rooms have incorrect wiring and the power is supplied the other way around. A room with incorrect wiring receives power if and only if the master switch of its floor is if I turn the master switch on some rooms are going to get powered, and if I turn it off, the other rooms are going to get powered. So like it's more like there are two sets, so I can only pick one of those. Okay. There can be both correctly and incorrectly wired rooms on the same floor. For example, consider a floor has 4 rooms with correct wiring and 2 rooms with incorrect wiring. Okay. If the master switch of the floor and 2 rooms will not have power. If the master switch is off, will not have power and 2 rooms will have power. Okay, so in the different sets, we have one set has 4 rooms, other set has 2 rooms. We can really pick like which way to power. If we turn on the switch, 4 ohms will get power, and the other two will get power only if the switch is turned off. The company does not want to spend extra money to fix the wiring mistakes. Instead, they decide to first turn on all the master switches and then turn off exactly K of them to maximize the total number of rooms across all floors that will receive power. Okay. So this is a maximization problem. So we have to maximize something. Basically, there's a master switch in all of the floors. There will be multiple floors, and then for each floor the switch is turned on. So the correctly wired rooms are all powered, and then we have the option to turn off exactly K of those switches, and the goal is to maximize the rooms with power. Okay, I think the problem is clear. If something's not clear, just drop a text. Okay. So standard input. The first line has a single integer t, the number of test cases for each test case. The first line consists of 3 integers m, n, and k, where m is the number of floors in the hotel, n is the number of rooms per floor, and k is the exact number of master switches that will be turned off. Okay, so about the problems with test cases, usually, almost all the time, if there are multiple test cases, they are like completely independent. So when you're writing the code, like make sure to like write the solution code and the iterating test cases part separately. So it is gonna the code is gonna be like a little bit clearer. Give me a minute. Uh, okay, so for each test case, m and n k, okay, and for each of the next m lines, there is a single integer between 0 and n that indicates the number of rooms that are wired correctly on that floor. The output format is for each test case. Output a single line in the line, the maximum number. Okay. So there are t test cases. So we have to print t lines saying like the maximum number of rooms that may receive power. Okay, that's the input and output format. And about the constraints, number of test cases is less than 20, and k and m. K is the exact number of master switches that will be turned off, and m is the number of floors. Since there are only k floors, yeah, one switch per floor, so there can only be like less than m, less than or equal to m switches. So k is less than or equal to m. They can be 10 to the power 6 floors, and then what's n? Yeah, n is the number of rooms per floor. Okay. The sum of m all across test cases in the single test file is at most 2 into 10 to 6. So this line is given to say that if this wasn't given, m can be 2 into 10 to 7, right? Because there can be 20 test cases and each test case can have 10 to the 6. Then it's going to be 2 into 10 to 7. But since this constraint is given, the total can only be like 2 into 10 to 6. Yeah. Okay. let's also go through the examples. So first input. Okay, so this input file has two test cases. One is this, one is this. Let's go through the first one. M, N, and K. We have two floors and two rooms per floor. K means the number of switches we have to turn off. Okay, in the first one, there are two floors with two rooms in each floor. And on the first floor, both rooms, sorry, both rooms have correct wiring. And on the second floor, both rooms have incorrect wiring. Because here it's 2, because here is 0. Okay, we have to turn off one switch. If we turn off this switch, the other rooms are going to get lighted up, right? So here it's 0, so there are two rooms left. So if we turn off this switch, two rooms are going to get lighted up. 4. If we turn off that switch. If we turn off this switch, the stops and needs to like turn off the switch in the second floor. Okay, in the second test case, there are two floors with 4 rooms in each floor. On the first floor, all rooms have incorrect wiring. Okay, it's 0. And 3 have correct wire. In this room, 3 rooms have correct wiring and 1 has incorrect wiring. Since k equal to 2, okay, k equal to 2, so there are 2 rooms, we have to turn off all those. So when we turn off all those, here since this is 0, we have 4 rooms in the other set. So here we are gonna get 4 rooms, and when we turn off these 3, 1 room left from the all 4, there's 1, 4 plus 1, 5. The output here is 5. Is that clear? And does anybody have any like idea on how to solve? Like maybe like a couple minutes and think how to solve this. Th- Is anyone thinking like, does anyone need more time? Or should I go to explain? Yeah, okay, I'll go straight to explaining then. Hmm. Okay. So, this is annoying. Okay, so how do I say this? So there are n floors. Wait, I have something nice. How can I rotate this? Okay. Okay, so our hotel is horizontal. Uh, no, we, uh, okay, so each floor has that looks shit. Okay, nice. Each floor has n rooms. Each floor has n rooms, and then I don't remember the statement. Okay, so we have an m floors. Okay, so the thing is, initially we have the all the master switches are turned on. So is will be getting power. So we have to make a choice. But let's first see like assess our initial situation. So uh first we can get this we can get the total number of powered up rooms by just summing up the correct value. Uh, we have to make a choice. We have to select k of those floors and flip the switch, like turn off the switch. So the goal here is to like maximize. Goal here is to maximize the number of rooms with power. So when we are flipping off each switch, we have to make sure that we are getting some benefits of it. So imagine if a floor has C switches, C number of switches. Let me zoom in. Okay. Each floor has not each floor, like let's get one floor, and then that floor has C rooms that are correctly wired. So if the switch is turned on, we are gonna get C rooms. But if the switch is turned off, we are gonna get the rest of the rooms, that is n minus C. This when the switch is turned on, and this when the switch is turned off. So we have to make a choice that what if we turn off this switch, are we gonna get something out of it? Like what's gonna happen? So if we flip the switch, we are gonna lose these C rooms and we are gonna get these n minus C rooms. So the total is the total difference will be we are gonna receive n minus C rooms to our total, but we are also gonna lose C rooms. So this equals to n minus 2C. So for a floor, if this is the number of rooms we are gonna get if we flip off the switch. So if this number is positive, our total number of rooms will increase. If this number is negative, total number of rooms will decrease. Yeah. So, and also, since we have to maximize the number of rooms we are going to get, what we have to do is we have to pick rooms such that this number is going to be maximum. So the maximum this number is, the more rooms we are going to get for our total. So what we can do is calculate this number for all the rooms and then sort our array by that, and then pick the first k because that's the most optimal and flip off those switches. Is that clear? Like, if it's not clear, you can ask something. If it is not clear, ask. I'll just go straight to the implementation. Okay, I'm writing C++. But I think most of you will be writing Python. I don't know that much Python. Yeah, we'll try. Okay, so what's the input? We are gonna get the number of test cases, and then we are gonna solve the problem for all those test cases. Hey, yeah, like I said, I don't write that much Python. We don't need this. Solve. Okay. So for each line, we are gonna get M and N and K. Mhm. And then for each of the next M lines, a single integer between 0 and N. Right. Let's keep that as C. I think there's a thing called list. Yeah, right. Oh, I in range. There are M numbers, and we need to append to C. Oh, no, let's get C underscore. We'll get number. We are gonna get the number of rooms with power, and then append this to C. And then I have to sort the list by what we discussed, n minus 2c, right? Is the sort in place? I don't know. Wait, let me Google. Like this, right? Yeah, okay, so we are sorting by n minus 2c. Yeah, okay. So in the last session, I said when we have to do some like some kind of like a different sort. We don't have like write a sort algorithm by ourselves. Or in this case, we can do this by like also creating another list of C. But we can use, I said we can use a custom comparator. What I'm doing here is using a custom comparator. Here, instead of sorting like the list of numbers by just those numbers, I'm sorting them by the n-2c value of it. Okay, we have sorted. I'm already reading using Python. We have to pick k numbers, or else we can loop to all the numbers and let's keep a sum. And if that means we are going to flip the switch. So I'm going to append this by n minus. So this, or else I'm going to append this by the switch is going to stay the same. Okay, we can, there's a print statement, I think. Okay, how's it gonna go? Well, apparently I can't use. There's no minus in the Python. Something's wrong. Was it the way I got inputs? I have to get M and N and K. Can anyone see what's wrong? Yeah, okay, we'll have to debug. Can't I see the output? Okay. Okay. How we see none type? Oh wait, maybe the sort is in place. The sort is in place. Okay, so the thing I did wrong was, this is basically, I don't know that much C++, sorry, that much Python. So the sort function of a list does not return anything. It just sort the list in place. So when I was setting C equals C dot sort, then it got return. Since it doesn't return anything, C got none. Okay, then we can submit. Didn't work. Okay, I'm getting this. Oh, no. It works. Yeah, okay, I got 100. So that was the solution. I think that was pretty easy. Does anybody have any questions? If no one has questions, we can move on to the next problem. Okay, I spent way too much time on this. The next problem was the binary search one. Oh. Yeah. This one. Okay, this is an interesting problem. This is harder than the searching problem. Okay, so let's get to it. Okay, today Jaravi, weird name, had a, let's call him or her J. Today J had a job interview for a very important tech company. The interviewer asked him to solve the next problem. Given a string S, the length of S is less than 10 to the power 6. Answer Q queries. Q is less than 5 into 10 to the power 4. For each query, he received a string P. String Pi, the length of the given string is less than 100, and he had determined the size of the longest suffix of Pi. So suffix is like it's like a part of the string, a part of a continuous substring starting from the end of that string, which is a subsequence of S. Subsequence is like when you're given a sequence and you can ditch some of those numbers and then get like a subset of those elements, but that subset has to be continuous. For an example, this X, A, Y, B, A, B, A, X, B, B is a subsequence, A, Y, B is a subsequence, A, X, Y is not a subsequence because the order is different. That's what a subsequence is. Unfortunately, Jay could not solve the task, so he wants to know if you can solve it. Okay, so this problem doesn't have that much of a story. It's a straightforward problem. Okay, basically what you have to do is you are given a string S and you have to answer Q queries. For each query, you are given a string and you have to like find the longest suffix such that that suffix also exists as a subsequence of the string S. Okay, the standard input format is like, okay, we are going to get the string S and the second line contains the number of queries and then each of the queries contain a string P. Okay, for each query, you need to print the size of the longest suffix Pi, which is subsequence of S. Okay, so the constraints are already given here. Okay, so for almost all problems, there's like a naive way to solve it. It's not the most efficient one, but we can get an idea about the problem by solving it that way. If it's like too straightforward, you don't have to implement it, but sometimes it helps. So the naive solution is we have the string, and we can like go through all the strings, p strings, and then we can iterate through all the suffixes, like from starting from the end, and then check if those suffix, that substring, is a subsequence of the string s. We can just check that. So so the naive solution, I've actually, this is some code I generated for the naive solution. So basically, for the naive solution, we have to do is the only complicated part is like figuring out if a string is a subsequence of some string. I'll explain that algorithm first. So what we're gonna do is to see if some string is a subsequence. Wait, it's easier if I draw. Let me find a sample. Let's get this. And the subsequence could be XBA. Okay, so this is how we are gonna see if this string is a subsequence of this string. So basically, if this is subsequence, we can like ditch some of the characters in this, and we should be able to reach this string. So as you can see, like if we ditch this and this, we are gonna get A, B, and then if we ditch this and this, we are gonna get A. So X, B, A. Yeah, we can do that. But the deterministic algorithm is, okay, we are gonna keep a pointer here, and we are gonna keep a pointer here. So we are first gonna see if these two pointers match. So that means this is the same number. So we are extracting a subsequence from this string, right? From this subsequence, we can use this character in the subsequence because those are equal. And then, okay, x equals x. What we are going to do then is we are going to move this pointer here. Okay, we are going to move this pointer here and compare it with this. Oh no, so here we have x, so we can move this we can move this pointer here also. So the reason is since these two characters match, we can use this character as a this character in the extracted subsequence. So from that point, we are interested in from the next character. So we are going to go to B, and we are going to compare with A, but it's not equal. So we will have to definitely ditch that when we're extracting subsequent. So we are going to move the pointer here. We are not going to move this pointer because we still didn't find a B yet. And then here it's also not equal. We are going to move the pointer here. Okay, then now we found a B. So we can use this. So we have to ignore this, but we can use this in the subsequent. And then since it's equal, we can move it here, we can move it here. And we are going to check, okay, we also have the same one. So we can use this, and then we can just ignore the other parts. So that's how we basically like find if some string is a subsequence of some other string by like keeping two pointers and moving them together. I hope that was clear. If it's not clear, drop a text. So here is the implemented version of that. So ij is the pointers. Initially, those are in the 0. So we can only iterate like the lengths until the string lasts. So we are gonna iterate that while I is less than the length of S and J is less than the length of P. And since since we are comparing each of the characters in the substring, we'll be moving the pointer anyways. So in each iteration of the loop, we are going to be increasing the I, and we are going to only increase J only if we have a match. So that increasing J means, okay, we can use that as the subsequence, as that character as the part of the subsequence. So we are going to check if those characters match. If they match, we can move the J pointer. But if not, we are not incrementing that. We are just moving the I. So by the end of this loop, J means the pointer of this has to reach the end of the string. It reached the end of the string means we got matching characters from this string in the correct order. So that means we have found a subsequence. If J equals to the length of P, that means we have found a subsequence. If not, we have not found a subsequence. So that's how this E subsequence function works. Okay, then what we're basically going to do is we are going to take inputs. Yeah, so yeah, we are going to take this is the string S, this is Q is the number of queries, and then so this array part is, I think this is generated code. So they read the entire input file and then they split it by byte space, and then then they are accessing those information based on indexes. So we have S and Q and the queries as an array. So for each query, we are going to keep the max length we found so far as 0. So we are gonna iterate from the end, from the length to 0. And this is the suffix. Suffix is a substring, continuous substring till the end of the string, right? So we are going to go through each of the suffixes, and then we are going to like go through this solution and check if the substring, if that suffix is a subsequence of string S. And then what we're going to do is we know so that length if it is if that subsequence is if that substring is a subsequence of that, we can use that length for the answer. So what we are going to do is we are going to loop through all those and find the maximum and then print that maximum for each of the queries. So that is a naive solution. So the issue with this solution is length of the string S is 10 to the power 6. And then this is subsequence algorithm. We are going through the entire string. So in the worst case, it's also a linear algorithm. So linear means it's also gonna get 10 to the power 6 operations. So each query will take 10 to the power 6 operations, and there are 5 into 10 to the power 4 queries. So that means 5 into 10 to the power 10. That is way too long. So you're not going to be able to solve that in, we have 5,000 milliseconds, so that means 5 seconds. That's a long time, but still like 10 to the power 10 is like an extremely large number. Because if we say we can do 10 to the power 8 in a second, then we have 200. So 10 to the power 2 is 100. That means like approximately 2 minutes. So the code is going to run for like 2 minutes. So, but we can get some kind of points for this. I'm going to run the examples. Okay, I'm going to submit it. Yeah, it's lagging. Yeah, it's going to get time limit exceeded because this algorithm is not that fast. You guys, as you can see, yeah, you're not going to pass from now. Okay, then we'll use binary search for the optimized solution. Mhm. So this is kind of hard, the binary search part. So basically, the logic there is uh, wait. So basically, if we are given a substring, the way to find if you're given a string, the way to find that if that string is a subsequence of another string is like for each of those elements, we have to pick an element from that big string, and also the elements we pick must be in like the correct order, right? That's the problem statement, and that's the definition of a subsequence. So what we are going to do is we are going to do some pre-processing. What we are going to do is for each of the characters we find in the smaller string, we are going to see where can we find those strings in the large string. We are going to keep those indices. So for an example, for x, we can find it in the 0th index. That's all. For B, we can find it in 0, 1, 2, 3, 4, 3, and 5. For A, we can find it in 0, 1, 2, 3, 4, 5, 6. So these are the indices we can find each of those elements, right? Each of those characters. So if we were to find a subsequence, we'll have to pick indices from this. Like we have to pick one of these x, one of these b, one of these a, and the other constraint is all those numbers have to be like in the ascending order, because like imagine we for this b element we picked 5. If so, we can't pick the first a because like that a is like before b, but here b a is after b, so we have to maintain the order. So if we keep like if we keep track of the indices of occurrences of those characters, uh, the problem boils down to picking up one integer, one index from each of those characters, and they have to be in the correct order. Yeah, so is that part clear? If it's not, you can ask. Okay, I think it's clear. It's either like super clear or not clear for anyone. Okay, we have a clear message. Okay, nice. Yeah, happy. Uh, so yeah, so in this step, actually, we can use binary search. After like transforming this problem to this state, that's how we are gonna apply binary search. So initially, the time complexity was linear because we were going through the entire array. So we are going to reduce that to log n, the time complexity of binary search. The way we are going to do is we are going to keep the like current index we are checking in the big array. So at the first, it's -1, let's say, and what we are going to do is, for each of these arrays, we need a number that is greater than this number. And we can pick any of those numbers that are greater than the current index we have, but it's optimal to find like the smallest number, because then there will be the most space left in the big array. So we won't lose any chances. So what we want to do is, we are going to keep track of the current index we are checking. At the moment, we are not checking anything like at start, so it's going to be like -1. And then from each of those arrays, we are going to pick the first number that is greater than this. So X array only has one number, and that's 0. That is greater than -1. So we are going to keep that. And then in the array B, we can pick either of those. Not either of those. The smallest number that is greater than 0 is 3. So we are going to get 3. And then in this array, the smallest number greater than 3 is 4. We can pick that. So I don't know if you remember, but I said something about the lower bounds and upper bound. So in C++, you have this lower bound function and upper bound function. If I say the definition of lower bound, I think, yeah, wait. Element in the range. Okay, if you search the lower bound, you're gonna get this. So basically, if you're searching for some number, by getting the lower bound, you can get the first occurrence that is equal to that number. So yeah. So when I was explaining, I picked -1 as the start, and then was appending numbers from the beginning to the end. So we picked from -1, we picked 0, and then 3, and then 4. So we can do the same thing from the other side. So when we are going from that side, we are going to pick the largest number that is smaller than what we have. So we are doing the same thing. We are building the subsequence from the end. So the reason we are doing that is, we can use this lower bound function, because with this lower bound function, we can find the first occurrence of in some character. Not character, we are dealing with indices here. So first occurrence of that index. So we can find like the largest element smaller than that by just decrementing the index. So we can use the built-in function that's why you doing it from the end. So yeah, I think it's clear how to use this lower bound function to do this. The thing is, when we do it this way, since this is on the Latin alphabet, there are 26 letters, and then for yeah, there will be 26 different arrays of this, and the length of all the elements, the sum of the lengths of all the elements will be the sum of the length of this element. And also, since the binary search time complexity is log n, and the sum of those arrays is less than 10 to the power 6, the time complexity of these operations is going to be also approximately log base 2 of 10 to the power 6. So initially, what we did from linear complexity, we can do this now in logarithmic complexity. Was that clear? I think it's clear. We can move on to writing the code. If it's not clear, let me know. Okay, we only got 33 points. I have a pre-written code for that. I'm not gonna try writing Python again. I don't want to embarrass myself again. I don't have a Python code. Okay, I do. Okay, let me explain it. So the way it takes input is also the same as the previous one. Yeah, they are going to read the entire input and then access those values from the indices. And there's this library called bisect. The upper bound and lower bound functions from C++ exist in the standard library. But for this, you will have to use this bisect library. And then we are going to keep a list of lists for to keep these arrays, the character indices thing. Since there are 26 characters, we are going to need 26 of those. And then what we are going to do is we are going to iterate to the string s, and then the syntax is we are going to get the integer value of a character and then subtract it by the integer value of a. So we are going to get integers such that for character a we are going to get 0, for character b we are going to get 1, for character c we are going to get 3 until z has 26. So what we are doing here, this is what we're doing here. And then for all of those characters, we are gonna append this index. So we found this character, so we are going to figure out the index of the character array, and then we are going to append the index for that. So here we are making this array, and then for each of the queries, what we are going to do is initially when I was explaining, I was going from the start, so I got 0, minus, and like -1. Since we are using that lower bound function and we are going from the end, we are going to keep the current position as the length of the string. So we are going to iterate for each character from the suffix, like the reverse. We are going to reverse the p array string and iterate from the end because we are dealing with the suffixes. And like we did here, we are going to get the index. And if we haven't found any characters of this type in the original string s, we are going to break because we won't be able to find the solution. Yeah. So here with count, we are going to keep like the length of the suffix we are going to get. So wait. Yeah, we are going to keep the length of the suffix. And we have to, okay. So here's the position list that we are currently working on. So like if I was focusing on this B, we have to work on the occurrences of that. So if I was working on B, I will be focusing on this array. So we are going to get that position list array. And then this bisect left is basically the same as lower bound. We are going to do a search on the lower bound on position list for the current position. And then the current position is the sm- like the earliest occurrence of that number. So since we are focused on the greatest element less than that element, what we are going to do is we are going to do this bisect thing and figure out what the lower bound is. If the lower bound is 0, that means there are no elements before that. We have to break the loop, or else we are going to update the current position by lower bound -1. And then if we reached here, that means we have found the subsequence until that suffix. So we are going to just increase the count. So yeah, either from here or here, we are going to break the loop when we can't find the subsequence for that suffix. So we'll have like keep what we did so far as the longest suffix. So we are going to do the loop. We are going to do this loop until the end of the string p. And then after that, we are going to print the count. Here count means like the characters matched from the end. So that's going to be the longest suffix we found so far. And for each of the queries, we are going to print that. Okay, I'm going to run this on examples. Okay. Okay, yeah, we got 100. Okay, we did the binary search thing. Here we didn't implement binary search by hand. We like changed the problem, like transformed the problem a little bit. So we could use the lower bound operation. Yeah, like I said in the last session, like when implementing binary search, it's easier to get some things wrong. So better to use a function like this when you can. So that's how we solve a binary search problem. And we also did the sorting problem. So that's it for today. If you have any questions, you can ask. Okay, I didn't get any questions, so I think everything's clear or nothing's clear. Yeah, I guess.
Thank you so much, Mr. Lakshith, for yet another insightful and enriching session. Your ability to explain complex concepts in such a clear and practical way continues to add immense value to this series. We truly appreciate the time and effort you've invested now across 3 sessions with our growing CodeX community. Your guidance has played a key role in helping our participants strengthen their problem-solving skills and build confidence in competitive programming. On behalf of the IEEE CodeX Sri Lanka team, we'd like to extend our heartfelt thanks to Mr. Lakshith Nishshanke by presenting this token of appreciation in recognition of your continued support and contribution. Your clarity of instruction and dedication to uplifting young programmers are truly commendable. Once again, thank you very much. If you haven't registered yet for the IEEE CodeX Sri Lanka session series, head over to our official website where you can learn more about the series and access session updates. Scan the QR code now and complete your registration to unlock full access. Also, stay connected with your peers and receive timely updates by joining our WhatsApp and Discord groups. You can engage with the community, ask questions, and grow together. QR codes are now displayed on the screen, so feel free to scan them and join in. That wraps up another impactful session of the CodeX Sri Lanka series. We have so many exciting workshops and sessions lined up in the coming weeks, so stay tuned and keep an eye on our communication channels for updates. Thank you for showing up, participating, and continuously pushing your boundaries. Each step you take with CodeX brings you closer to becoming the confident coder you aspire to be. I'm Sinaya, signing off on behalf of the IEEE CodeX Sri Lanka team. Until next time, stay curious, stay consistent, and keep solving. Good night, everyone, and thank you once again.